Back to the CryptoZombies coding tutorial, where we are exploring the intersection of voice first artificial intelligent technology and the blockchain and cryptocurrencies, looking at Solidity, which is the programming language for smart contracts on Ethereum. Today is lesson 3, advanced Solidity concepts. If you want to learn more about CryptoZombies, you can just look it up. These tutorials are entirely free. Let's get started. Advanced Solidity concepts are what we're going to be covering today. Now that we've got some experience coding on Solidity, we're going to dive into some of the more technical aspects of Ethereum development. It's going to be a little less flashy with no plot twists, but we will learn some really important concepts, getting us closer to building real dApps, like the contract ownership, gas cost, code optimization, and security. You've been warned, no kitties and rainbows in lesson 3, but a lot of densely packed Solidity knowledge in this lesson. We strongly recommend you complete lesson 2 before starting this one. We've got 14 lessons today, and it looks like we're picking up where we left off. Up until now, Solidity has looked quite similar to other languages like JavaScript, but there are a number of ways that Ethereum dApps are actually quite different from normal applications. To start with, after you deploy a contract in Ethereum, it's immutable, which means it can never be modified or updated again. This reminds me of a podcast I was listening to this morning on Software Engineering Daily that discussed continuous integration pipelines for smart contracts and potentially having proxy contracts that allow us to reference different versions of smart contracts depending on the latest version. The initial code you deploy to the contract is there to stay permanently on the blockchain. This is one reason security is such a huge concern on Solidity. If there's a flaw in your contract code, there's no way for you to patch it later. You would have to tell your users to start using a different smart contract address that has the fix. But this is also a feature of smart contracts. The code is law. If you read the code of a smart contract and verify it, you can be sure that every time you call a function, it's going to do exactly what the code says it will do. No one can later change that function and give you unexpected results. That's awesome. So sometimes we have devs that will push to our production environment accidentally, which will ruin the experience for our users. However, one of the nice things about immutability is there's no chance that someone overwrites our code. This is a fundamental difference between traditional coding in Web 2.0 technologies, where it's all mutable and it can constantly be copied, changed, erased, modified, and Web 3.0, where code is law, it's immutable. Once it's published on the blockchain, you're not changing it. External dependencies. In lesson 2, we hard-coded the CryptoKitties contract address into our dApp. But what happens if the CryptoKitties contract had a bug and someone destroyed all the kitties? It's unlikely, but if this did happen, it would render our dApp completely useless. Our dApp would point to a hard-coded address that no longer returned any kitties. Our zombies would be unable to feed on kitties, and we'd be unable to modify our contract to fix it. For this reason, it often makes sense to have functions that allow you to update key portions of the dApp. This sounds exciting and reminds me of the proxy that I was just talking about, the proxy smart contract. For example, instead of hard-coding the CryptoKitties contract, we should probably have set kitty contact address function that lets us change this address in the future in case something happens to the CryptoKitties contract. Okay. This seems contradictory to the fundamental philosophy that code is law and we don't want to modify anything. However, it does seem nice that we can introduce a setter function that would allow us to set key portions of our contract, of our dApp. Let's put it to the test. Let's update our code from lesson 2 to be able to change the CryptoKitties contract address. Delete the line of code where we hard-coded CK address. Change the line where we created kitty contract to just declare the variable, i.e. don't set it to anything. Create a function called setKittyContractAddress. It will take one argument of address, and it should be an external function, which means we can't call it internally. It's not private, it's public, and the only people that can call it are people in contracts outside of this contract. Inside the function, add one line of code that sets kitty contract equal to kitty interface address. Interesting. If you notice a security loophole with this function, don't worry, we'll fix it in the next chapter. Okay. Number 1, delete the line of code where we hard-coded CK address. Boom. Removed. Change the line where we created kitty contract to just declare the variable. Don't set it equal to anything. Delete it. Don't set it equal to anything. Create a function called set kitty contract address. It will take one argument of address, and it should be an external function. Let's go ahead and do that. I like having the separation between days, but I'll code a little bit before I give some reflection. Function set kitty contract address. Inside of here we want an address underscore address, and then we want an external function. Should be good to define the contract. Create a function, it will take one argument, should be external. Inside the function, add one line of code that sets kitty contract equal to kitty interface of address. So now we want kitty contract equal to kitty interface of underscore address. Let's check it. Awesome. Awesome, awesome, awesome. I like having the separation of days in between my learning. In the past, I've gone 0 to 100 and I've gone through an entire course in a day. But I think breaking this up into doing one chapter each day or one lesson each day has made it so that there's a little bit more time for this lesson to actually get ingrained into my deeper knowledge, rather than just a cram and dump method that was pretty typical for me in college and high school. A more long-term sustainable learning method is more of a method following Kaizen, where you do 1% every day and try to build the habit and really ingrain the knowledge over a longer period of time instead of trying to cram it all into one day. I don't want to sign in. Chapter 2, Ownable Contracts. Did you spot the security hole? Set kitty address is external so anyone can call it. That means anyone who called the function could change the address of the CryptoKitties contract and break our app for all its users. We do want the ability to update this address in our contract, but we don't want everybody to be able to update it. To handle cases like this, one common practice that has emerged is to make contracts ownable, meaning they have an owner U who has special privileges. That's great. Open Zeppelin's Ownable Contract. Below is an ownable contract taken from the Open Zeppelin Solidity library. Open Zeppelin is a library of secure and community-vetted smart contracts that you can use in your own dApps. After this lesson, we highly recommend you check out the site for further learning. Let's quickly look up Open Zeppelin. The standard for secure blockchain applications. Open Zeppelin provides security products to build, automate, and operate decentralized applications. We also protect leading organizations by performing security audits on their system and products. Looks like Coinbase uses them, Brave, Augur, Compound. Cool. Cool. Good to know. I like that this site also introduces actual technologies. Like yesterday we looked at CryptoKitties. So it's showing us and getting us exposed to other applications that are already built on top of blockchain Web3 technologies. Given the contract below as a read-through, you're going to see a few things we haven't learned yet, but don't worry, we'll talk about them afterward. In Ownable Contract, we have a private address of owner. We have an event called ownership transferred. And we have to put in the previous owner as well as the new owner. Then we have a constructor where the owner is whoever is contacting this smart contract, and when this contract is started, we emit the owner transfer ship by using address 0, which is supposedly stored in memory, and then owner. Okay. Return the owner. Owner returns whoever the owner is. Owner we can set only owner, throws if called by an account other than the owner, returns true if message sender is the owner, is owner, then checks if message sender equals owner. I like how short these functions are. These really encapsulate clean code of each function should do just one thing. If it does more than one thing, like only owner, you then split the rest of it out into its own function so that everything stays small. Allows the current owner to relinquish control of the contract. Renouncing to ownership will leave the contract without an owner. It will not be possible to call the function with the only owner modifier anymore. Only owner. Ownership transferred. Okay, we're just going to give this a quick read through. Transfer ownership, we give a new owner. Public only owner, this makes me think it can only be called by the owner. I'm not sure how this only owner works, but it probably calls this function before doing our function. Transfer ownership requires new owner, does not equal address 0, so requires that the new owner is not the existing owner. Ownership transferred, so then we emit that the event happened. It's interesting that we emit the event before we actually assign it. I would expect that we would assign the new owner to the owner value before we emit the event, but that's beside the point. A few things to note we haven't seen before. Constructors. That's a constructor, which is an optional special function that has the same name as the contract. Here is our constructor. Where's our function ownable? I don't see a function called ownable. It's referencing this, but I don't see it. It will get executed only one time when the contract is first created. Function modifiers, modifier only owner. Modifiers, oh, I didn't even see a modifier. Modifier, interesting. Throws if called, okay, let's see what that modifier. Modifiers are kind of half functions that are used to modify other functions, usually to check some requirement prior to execution. In this case, only owner can be used to limit access, so only the owner of the contract can run the function. We'll talk more about function modifiers in the next chapter and what the weird underscore semicolon does. Yeah, what the heck does this do? Indexed keyword, don't worry about this one, we don't need it yet. Just so that I'm aware, where is indexed keyword even used? Indexed, where is it? I'm not, oh, here it is. Indexed. Yeah, I wonder what those index terms mean, but right now we're telling it not to use it. Okay, so the ownable contract basically does the following. When a contract is created, its constructor sets the owner to whoever deployed the contract. That's cool. It adds an only owner modifier, which can restrict access to certain functions to only the owner. It allows you to transfer the contract to a new owner. Only owner is such a common requirement for contracts that most Solidity dApps start with a copy and paste of this ownable contract, and then their first contract inherits it. Cool. Okay, so this is common. We'll probably be using this ownable contract inside of some of our own dApps. Since we want to limit setKitty contract address to only owner, we're going to do the same for our contract. Put it to the test. We've gone ahead and copied the code from the ownable contract into a new file, ownable.sol. Let's go ahead and make Zombie Factory inherit from it. Modify our code to import the contracts of ownable.sol. If you don't remember how to do it, take a look at the zombiefeeding.sol. Modify the Zombie Factory contract to inherit from ownable. Again, you can take a look at zombiefeeding.sol if you don't remember how this is done. Okay, we're in Zombie Factory. Let's import it. I believe it's just import ./ownable.sol. I think that's all we have to do to import it. Let's check. Yep, it's just import ./name of the file ending with a semicolon. Import ./name of the file ending with a semicolon. Step 1 done. Alright, what's next? Modify the Zombie Factory contract to inherit from ownable. Contract Zombie Factory, I think it's extends. Maybe it's inherits. Not sure if that's right. Let's check. Is. We just use the is. Is ownable. This looks right to me. Let's check it. Okay, so we just imported all of the ownable.sol smart contract into our Zombie Factory, which means that we can now, when the contract is deployed, it will set the owner to the owner. We can change the ownership, but still our setter function is not restricted to only the owner being able to modify it. I think we'll probably do that in the next chapter. Only owner function modifier. Okay, now that our base contract Zombie Factory inherits from ownable, we can use the only owner function modifier in our zombie feeding as well. This is because of how contract inheritance works. Remember, zombie feeding is a Zombie Factory and Zombie Factory is ownable, so inheritance chains together. Thus, zombie feeding is also ownable and can access the functions, events, and modifiers from the ownable contract. This applies to any contracts that inherit from zombie feeding in the future as well. It's very cool. Function modifiers. A function modifier looks just like a function, but uses the keyword modifier instead of the keyword function. And it can't be called directly like a function can. Instead, we can attach the modifier's name at the end of a function definition to change that function's behavior. Let's take a closer look by examining only owner. So, looking at only owner, we require isOwner, and isOwner just returns whether or not the person calling the contract is in fact the owner, which is a registered value on the blockchain. Notice the only owner modifier on the renounce ownership function. Let's see the renounce ownership. Allows the current only to relinquish control of the contract. It leaves the contract without an owner. It will not be possible to call the function with the only owner modifier anymore. So, we then set the owner to address 0, and we add the only owner modifier to the function so that this gets called and run before this function executes. When you call renounce ownership, the code inside only owner executes first. Then, when it hits the underscore semicolon statement, it goes back and executes the code inside renounce ownership. So I guess this line is pretty much like a return statement, but because it's a modifier, it doesn't return anything. It just tells the caller function that we're done executing. So while there are other ways you can use modifiers, one of the most common use cases is to add a quick require check before a function executes. In the case of only owner, adding this modifier to a function makes it so only the owner of the contract, aka you, if you deployed it, can call that function. Note, giving the owner special powers over the contract like this is often necessary, but it could also be used maliciously. For example, the owner could add a backdoor function that would allow him to transfer anyone's zombies to himself. That would be very poopy. So it's important to remember that just because a dApp is on Ethereum does not automatically mean it's decentralized. You have to actually read the full source code to make sure it's free of special controls by the owner that you need to potentially worry about. There's a careful balance as a developer between maintaining control over a dApp such that you can fix potential bugs and building an owner-less platform that your users can trust and to secure their data. I like that line. There's a careful balance as a developer, as us, the people building the smart contracts. There's a balance between us having control so that we can fix potential bugs and also just building an owner-less platform that we can use that users can use to secure their data. Let's put it to the test. Now we can restrict access to the setKitty contract address so that no one but us can modify it. This is what we were talking about at the end of the last chapter. Add the only owner modifier to the setKitty contract address. setKitty contract address, external, now we say only owner. And only owner is definable over here. The only owner modifier is, we can access it over here in zombie feeding because zombie feeding inherits the zombie factory. Zombie factory inherits the ownable, and inside of ownable we have this function only owner. This inheritance structure reminds me of old programming languages like C, where inheritance is kind of chained in a very long set. But it feels different from JavaScript, where in JavaScript we would need to, in JavaScript we typically inherit functions manually. When we inherit something, we typically don't get every single function and attribute from inside of that function. We typically have to manually import variables that we export from the original. It's interesting to learn about how Solidity works. So let's check. We got it. Next chapter. Alright, I don't have this info, so I don't have an account. I guess I could add one, but I'm not going to do that on this live stream. Chapter 4, Gas. Great, now that we know how to update key portions of the dApp while preventing other users from messing with our contracts, let's look at another way Solidity is quite different from other programming languages. Gas, the fuel Ethereum dApps run on. In Solidity, your users have to pay every time they execute a function on your dApp using a currency called gas. Yeesh. They have to pay every time they execute a function in your dApp using a currency called gas. Users buy gas with Ether, so your users have to spend ETH in order to execute the functions in your dApp. That feels like a limiter, but also I don't know how much it costs to execute a function. How much gas is required to execute a function depends on how complex that function's logic is. So it depends on how complex the function's logic is. Each individual operation has a gas cost based roughly on how much computing resources will be required to perform that operation. Example, writing to storage is much more expensive than adding two integers. That makes sense. The total gas cost of your function is the sum of the gas costs of all the individual operations. This feels like calculus. The sum of the individuals. Each individual operation is the computing resource. So, interesting, let's keep moving. Because running functions costs real money for your users, code optimization is much more important in Ethereum than in other programming languages. If your code is sloppy, your users are going to have to pay a premium to execute your functions, and this could add up to millions of dollars in unnecessary fees across thousands of users. Why gas is necessary. Ethereum is like a big, slow, but extremely secure computer. When you execute a function, every single node on the network needs to run the same function to verify its output. Thousands of nodes verifying every function execution is what makes Ethereum decentralized, and its data immutable and censorship resistant. The creators of Ethereum wanted to make sure someone couldn't clog up the network with an infinite loop, or hog all the network resources with really intensive computations. So they made it so transactions aren't free and users have to pay for computation time as well as storage. Note, this isn't necessarily true for other blockchain like the ones the CryptoZombie authors are building at Loom Network. it probably won't ever make sense to run a game like World of Warcraft directly on the Ethereum mainnet. The gas costs would be prohibitively expensive, but it could run on a blockchain with a different consensus algorithm. We'll talk more about what types of dApps you'd want to deploy on Loom versus the Ethereum mainnet in a future lesson. I'm excited for that lesson. Packing to save gas. In lesson 1, we mentioned there are other types of UINTs, UN8, 16, and 32. Normally there's no benefit to using these subtypes because Solidity reserves 256 bits of storage regardless of the UINT size. For example, using UINT8 instead of UINT256 won't save you any gas. But there's an exception to this inside structs. If you have multiple UINTs inside a struct, using a smaller sized UINT when possible will allow Solidity to pack these variables together and take up less storage. For example, normal struct, mini-me uses less. Mini will cost less gas than normal because of struct packing. Got it. For this reason, inside a struct you'll want to use the smallest integer subtypes you can get away with. You'll also want to cluster identical data types together, i.e. put them next to each other in the struct so that Solidity can minimize the required storage space. For example, a struct with UINTs C, UINT A, UINT B will cost less gas than a struct with fields UINT32, UINT, and UINT32 because UINT32 fields are clustered together. Put it to the test. In this lesson, we're going to add 2 new features to our zombies, level and ready time. The latter will be used to implement a cooldown timer to limit how often a zombie can feed. So let's jump back to zombiefactory.sol. Add 2 more properties to our zombie struct, a level and a ready time. We want to pack these data types together, so let's put them at the end of the struct. 32 bits is more than enough to hold the zombie's level and timestamp, so this will save us some gas costs by packing the data more tightly than using a regular UINT. We're now going to add 2 UINT 32s. One of them is going to be called level. One of them is a UINT 32 called ready time. Check. Chapter 5, Time Units. The level property is pretty self-explanatory. Later on, when we create a battle system, zombies who win more battles will level up over time and get access to more abilities. The ready time property requires a bit more explanation. The goal is to add a cooldown period, an amount of time a zombie has to wait after feeding or attacking before it's allowed to feed or attack again. Without this, the zombie could attack and multiply 1,000 times per day, which would make the game way too easy. In order to keep track of how much time a zombie has to wait until it can attack again, we will use Solidity's time units. Solidity provides some native units for dealing with time. The variable now will return the current Unix timestamp of the latest block. The number of seconds that have passed since January 1st, 1970. The Unix time as I write this is that time. Okay. Unix time is traditionally stored in a 32-bit number. This will lead to the year 2038 problem when 32-bit Unix timestamps will overflow and break a lot of legacy systems. So if we wanted our dApp to keep running 20 years from now, we could use a 64-bit number instead, but our users would have to spend a lot more gas to use our dApp in the meantime to sign decisions. Solidity also contains time units seconds, minutes, hours, days, weeks, and years. These will convert to a UINT of the number of seconds in that length of time. So 1 minute is 60, 1 hours is 3600, 1 days is 86,400. Number of seconds, so a year, it'll convert year to seconds. Hour converts hour to seconds. Here's an example of how these time units can be useful. Set last updated to now. Update timestamp, we set last updated. A storage variable that's stored on the blockchain, we update it to now, which is the number of milliseconds of the current block. 5 minutes have passed. Return now is greater than or equal to last updated plus 5 minutes. This converts 5 minutes to seconds. We then take last updated, which is a timestamp of a number of seconds. We add the number of seconds, and then we compare if now is greater than last updated plus 5 minutes. We can use these time units in our zombie cooldown function. Put it to the test. Let's add a cooldown time to our DApp and make it so zombies have to wait 1 day after attacking or feeding to attack it again. Declare a uint called cooldown time. Set it equal to 1 day. Forgive the poor grammar. If you set it equal to 1 day, it won't compile. That's funny. Since we added a level and ready time to our zombie struct in the previous chapter, we need to update the create zombie to use the correct number of arguments when we create a new zombie struct. Update the zombies.push line of code to add 2 more arguments, 1 for level and uint 32 now plus cooldown time for ready time. Note the uint 32 is necessary because now returns a uint 256 by default, so we need to explicitly convert it to a uint 32. Now plus cooldown time will equal the current Unix timestamp in seconds plus the number of seconds in 1 day, which will equal the Unix timestamp 1 day from now. Later we can compare to see if the zombie's ready time is greater than now to see if enough time has passed to use the zombie again. We'll implement the functionality to limit actions based on ready time in the next chapter. Start with number 1. Declare a uint called cooldown time. Uint cooldown time. Set it equal to 1 day. Since we added a level to our ready time, to our zombie struct, level and ready time, we'll need to update create zombie to use the correct number of arguments when we create a new zombie. Update the zombies.push to add 2 more arguments. We'll add 1 for level, and then ready time is going to be uint 32 of now, which is a registered variable, and then cooldown time, which we created up here, which is equal to 1 day. What did I mess up? Chapter 6, Zombie Cooldowns. Now that we have a ready time property on our zombie struct, let's jump to zombiefeeding.sol and implement a cooldown timer. We're going to modify our feed and multiply such that feeding triggers a zombie's cooldown and zombies can't feed on kitties until their cooldown period has passed. This will make it so zombies can't just feed on unlimited kitties and multiply all day. In the future, we'll add a battle functionality will make it so attacking other zombies also relies on the cooldown. First, we're going to define some helper functions that lets us set and check a zombie's ready time. Set and get. Passing structs as arguments. You can pass a storage pointer to a struct as an argument to a private or internal function. This is useful, for example, for passing around our zombie structs between functions. Zombie storage, zombie storage comes directly off the blockchain. Cool. Looks good. This way we can pass a reference to our zombie into a function instead of passing in a zombie ID and looking it up. Put it to the test. Start by defining a trigger cooldown function. It will take 1 argument, zombie, a zombie storage pointer. The function should be internal. The function body should set zombie.readyTime to uint 32 now plus cooldown time. Now create a function called isReady. This function will also take a zombie storage argument named zombie. It will be an internal view function and it'll return a bool. The function body should return zombie.readyTime is less than or equal to now, which will evaluate to either true or false. This function will tell us if enough time has passed since the last time the zombie is fed. Let's get started. We want a trigger cooldown function. Probably told us a place we want to define it. Function trigger cooldown. One argument, we want it to be a zombie. Storage underscore zombie. And we want this to be an internal function, which means it's private. It can be called by any other function or file within our smart contract. The body should set underscore zombie dot ready time equal to uint 32 of now plus, where's cooldown time? Cooldown time is defined inside of our zombie factory. Zombie feeding is a zombie factory, so we can still access cooldown time. Next, create a function called isReady. Function is underscore isReady. Function will also take a zombie storage argument named underscore zombie storage underscore zombie. Internal view, so we'll make it internal view. Returns bool. The body function should return underscore zombie dot ready time is less than or equal to now. We did something wrong. We'll call it a bool ready. Okay, I'm doing something wrong. Do you give me any info? Zombie.ready time. Did I get cooldown time wrong? Maybe it's because I forgot the semicolon. I forgot a semicolon. Chapter 7, Public Functions and Security. Now let's modify feed and multiply to take our cooldown timer into account. Looking back at this function, you can see we made it public in the previous lesson. An important security practice is to examine all your public and external functions and try to think of ways users might abuse them. Remember, unless these functions have a modifier like onlyOwner, any user can call them and pass them any data they want to. Re-examining this particular function, the user could call the function directly and pass in any target DNA or species they want to. This doesn't seem very game-like. We want them to follow our rules. On closer inspection, this function only needs to be called by feedOnKitty. So the easiest way to prevent these exploits is to make it internal. Put it to the test. Currently, feed and multiply is a public function. Let's make it internal so that the contract is more secure. We don't want users to be able to call this function with any DNA they want. Number 2, let's make feed and multiply take our cooldown time into account. First, after we look up myZombie, let's add a require statement that checks isReady and pass myZombie to it. That way the user can only execute this function if a zombie's cooldown time is over. At the end of the function, let's call trigger cooldown my zombie so that feeding triggers the zombie cooldown time. Alright, let's start. Feed and multiply is a public function. We want to make it internal. Feed and multiply, we want to make this an internal, which is similar to public, except only it can only be called by functions within our contract. Then let's make feed and multiply take our cooldown time into account. Let's add a require statement that checks is ready and pass my zombie to it. Okay. So now we'll say require underscore is ready, and is ready takes in a zombie element, so we'll pass in my zombie. So now, if it's not ready, it'll just throw an error and exit. If it is ready, we then are allowed to proceed to the rest of the function. At the end of the function, let's call trigger cooldown so that feeding triggers the zombie's cooldown time. Underscore trigger cooldown, and for trigger cooldown we also want to pass in a zombie, so we'll pass in the same zombie of my zombie. Should be good. Just past halfway. Chapter 8, more on function modifiers. Great. Our zombie now has a function cooldown timer. Next, we're going to add some additional helper methods. We've created a new file for you called zombiehelper.sol, which imports zombiefeeding.sol. This will help to keep our code organized. Let's make it so zombies gain special abilities after reaching a certain level. But in order to do that, first we'll need to learn a bit more about function modifiers. Function modifiers with arguments. Previously, we looked at a simple example of only owner, but function modifiers can take arguments. For example, modifier older than with an age and a user ID, we check that the age of user is greater than or equal to age. Must be older than 16 to drive a car, older than 16 with user ID. User ID is a parameter, so we take the parameter that's being passed into the function, we send that to our modifier, as well as a hard-coded value of 16. It's really cool. You can see here that I feel like this is making me think that database calls are going to be much faster on the blockchain than they were on traditional databases. Like right now, we use Firestore for a lot, and every time we want to make a database call, we either import our database library and then make asynchronous calls to that. That's pretty much what we do. And every single time we want to make a database call to write or read, we have to import the database with a security key and everything else. But with blockchain, it seems like authentication is kind of baked in from the ground up, and the database is on the computer itself, so we don't need an external database separate from where our code is executed. Where our code is executed is the database as well as our authentication layer. So it's got authentication, database, and computation all baked into the same coding framework. You can see here that the older than modifier takes an argument just like a function does, and that the drive car function passes its arguments to the modifier. Let's try making our own modifier that uses the zombie level property to restrict access to special abilities. Put it to the test. In zombie helper, create a modifier called above level. It will take two arguments, level, which is a uint, and zombie ID, which is also a uint. The body should check to make sure zombies of zombie ID.level is greater than or equal to level. Remember to have the last line of the modifier call the rest of the function with underscore semicolon. Start here. First thing we want to do, create a modifier called above level. It's going to have two arguments, a uint called underscore level, as well as a uint called underscore zombie ID. Inside the body, we want to make sure require zombies of the mapping underscore zombie ID and then the attribute of that zombie of level. This is a database call. This is such a simple database call. Is greater than or equal to underscore level. After we require that, we then allow the rest of the function to execute. Chapter 9, Zombie Modifiers. Now let's use our above level modifier to create some functions. Our game will have some incentives for people to level up their zombies. For zombies level 2 and higher, users will be able to change their name. For zombies level 20 and higher, users will be able to give them custom DNA. We'll implement these functions below. Here's the example code from the previous lesson for reference. A mapping to store a user's age. Mapping uint to uint, uint key, uint value, public, age. So we'll have a mapping of users' ages. Require that this user be older than a certain age, older than, it's a modifier, pass in an age and a user ID. We then look up from the age array of the user ID. It's got to be greater than or equal to the age that we're expecting. Must be older than 16 to drive a car, uses the older than, passes in 16 in the user's ID. Boom. Put it to the test. Create a function called change name. It will take 2 arguments, zombie ID and a new name. We'll make it external so that people outside of our smart contract can call it. It should have the above level modifier, which should pass in 2 for the level. Don't forget to also pass in the zombie ID. Note, call data is somehow similar to memory, but it's only available to external functions. Not sure what call data is, but I guess it's similar to memory. In this function, we need to verify that message.sender is equal to zombie to owner, zombie ID. So we'll use a require statement to enforce that check. 3, then the function should set the zombie's zombie ID name equal to new name so that we can change the name of our zombie. And then finally, number 4, we'll create another function called change DNA. Below change name, its definition and contents will be almost identical to change name, except the second argument will be new DNA instead of new name. And it should pass in 20 for the level parameter on the above level modifier. And of course, it should set the zombie's DNA to new DNA instead of setting the zombie's name. Alright, starting with number 1, we're going to create a new function called change name. So we'll use the function keyword and then the change name as the name of our function, passing in 2 arguments, a uint of underscore zombie ID, and then a string from and we're going to use call data instead of memory, called underscore new name. This is going to be an external function. And then we'll use our curly braces. In the function, we want to verify message sender is equal to zombie ID using a require statement. We also want the above level modifier. So we'll now say above level, and our above level needs a level number, which we will get from zombies underscore zombie ID dot level. And then we also need a the first one, we just want the level we're checking against. So the level we're checking against is 2, and then the zombie ID is just coming from our function parameters of zombie ID. Okay, so this is going to check that our level is above the level, and if it is, now we want to verify that message sender is equal to zombie to owner dot zombie ID. We'll use a require statement, so we will require that the zombie to owner of underscore zombie, the owner of the zombie is equal to message dot sender. Once we've enforced that requirement, then we should set zombies of underscore zombie ID dot name equal to underscore new name, which is going to then write to the blockchain the new name to our zombies array. Okay. Then we want another function called change DNA, which also has two arguments, a uint of underscore zombie ID and then a uint of underscore new DNA. It's also an external function. And then we want to make sure that we are above level, this time we want to be above level 20, and it's going to be, again, the zombie ID from our function parameter. Inside of here, we also want to require and make sure that the zombie's owner is the one that's the one requesting this, so zombie to owner of zombie ID should be equal to message.sender. If that's the case, then we can say zombies. We can rewrite to the blockchain. We can change the zombie ID dot DNA equal to underscore new DNA. And that should be all we have to do. But it's not. I did something wrong. Okay, I'm doing something wrong with the latter half of this. So message.sender is an address. Maybe we need to do keysack 256. Bro. One sec. Mosquitoes are eating me alive. I say go away to you. I don't want to kill you. I just want you to know you're not allowed to bite me while I'm coding. I'm not paying attention to you. I'm trying to pay attention to the audience and to the work at hand. Being mindful of what I am doing in the present moment. Okay. Keysack 256 message sender. Now let's do the same thing of zombie to owner. Keysack 256. So now we're comparing the hashes instead of comparing, and I'm just going to copy this. That wasn't it. So the answer was not doing that. Do I have any other checks where I'm... The double equal sign should work. Maybe we just should copy this require. I might just be putting them in the wrong order. Okay, I just had to change the order. Chapter 10. Saving gas with view functions. Awesome. Now we have some special abilities for higher level zombies to give our owners an incentive to level them up. We can add more of these later if we want to. Let's add one more function. Our DApp needs a method to view a user's entire zombie army. Let's call it getZombiesByOwner. This function will only need to read data from the blockchain, so we can make it a view function, which brings us to an important topic when talking about gas optimization. View functions don't cost gas. View functions don't cost any gas when they're called externally by a user. This is because view functions don't actually change anything on the blockchain, they only read the data. So marking a function with view tells Web3.js that it only needs to query your local Ethereum node to run the function. And it doesn't actually have to create a transaction on the blockchain, which would need to be run on every single node and cost gas. Interesting. So reading from the blockchain is free, but doing any writes or heavy computation costs gas. We'll cover setting up Web3.js on your own node later, But for now, the big takeaway is that you can optimize your dApp's gas usage for your users by using read-only external view functions whenever possible. Note, if a view function is called internally from another function in the same contract that is not a view function, it will still cost gas. This is because the other function creates a transaction on Ethereum and will still need to be verified from every node, so view functions are only free when they're called externally. Good to know. Put it to the test. We're going to implement a function that will return a user's entire zombie army. We can later call this function from Web3.js if we want to display a user's profile page with their entire army. This function's logic is a bit complicated, so it will take a few chapters to implement. Create a new function named getZombiesByOwner. It will take one argument, an address named owner. Let's make it an external view function so we can call it from Web3.js without needing any gas. The function should return a uint, an array of uints, as memory data location. Leave the function body empty for now, we'll fill it in the next chapter. Let's create a new function called getZombiesByOwner. Function. And inside of here we need an address called _owner. We want it to be an external view, so it can only be called outside of our contract. And external view means that it won't cost any gas to our users. This seems like a key type of function that we want to use as much as possible to reduce gas costs on our application. The function should returns uint array from memory. Chapter 11, storage is expensive. One of the more expensive operations in Solidity is using storage, particularly writes. This is because every time you write or change a piece of data, it's written permanently to the blockchain, forever. Thousands of nodes across the world need to store that data on their hard drives, and this amount of data keeps growing over time as the blockchain grows. This won't be true when sharding is introduced, but for now this is true, so there's a cost to doing that. In order to keep costs down, you want to avoid writing data to storage except when absolutely necessary. Sometimes this involves seemingly inefficient programming logic like rebuilding an army in memory every time a function is called instead of simply saving that array in a variable for quick lookups. Rebuilding an array in memory every time a function is called instead of simply saving that array in a variable for quick lookups. In most programming languages, looping over large data sets is expensive, but in Solidity, this is the cheaper way than using storage if it's an external view function, since view functions don't cost your users any gas. And gas costs your users real money. We'll go over for loops in the next chapter, but first let's go over how to declare arrays in memory. Declaring arrays in memory. You can use the memory keyword with arrays to create a new array inside a function without needing to write anything to storage. The array will only exist until the end of the function call, and this is a lot cheaper gas-wise than updating an array in storage. Free if its view function is called externally. Here's how to declare an array in memory. Function getArray external pure. Pure means it doesn't require anything outside of what is inside of this function, I believe, if I'm remembering right. It'll return the memory, a uint array. So then we create a memory of size 3. And then we set all the values to 1, 2, and 3 and return it. There's a trivial example just to show you how to use syntax, but in the next chapter we'll look at combining this with for loops for real use cases. Note, memory arrays must be created with a length argument. In this example 3, they cannot be resized like storage arrays with array.push, although this may be changed in a future version of Solidity. Put it to the test. In our getZombiesByOwner function, we want to return a uint array with all the zombies that our particular user owns. Declare a uint memory variable called result. set it equal to a new uint array. The length of the array should be however many zombies this owner owns, which we can look up from our mapping with owner zombie count owner. At the end of the function, return result. It's just an empty array right now, but in the next chapter, we'll fill it in. Let's start by going to our getZombiesByOwner function. Inside of that function, we want to declare a uint memory called result equals new uint array of size equal to owner zombie count. Owner zombie count of underscore owner should be all we need to do. Oh, at the end of the function, return result. Okay. Return result. There we go. We're now at level 12, for loops. In the previous chapter, we mentioned that sometimes you'll want to use a for loop to build the contents of an array in a function rather than simply saving that array to storage. Let's look at why. For our getZombiesByOwner function, a naive implementation would be to store a mapping of owners to zombie armies in the zombie factory contact. Owner to zombies. Then every time we create a new zombie, we would simply use owner to zombies to add it to that owner zombie array, and getZombiesByOwner would be a very straightforward function. Very easy. The problem with that approach. This approach is tempting for its simplicity, but let's look at what happens if we later add a function to transfer a zombie from one owner to another, which we'll definitely want to add in a later lesson. That transfer function would need to push the zombie to the new owner's owner to zombies array, remove the zombie from the old owner's owner to zombies array, shift every zombie in the older's own array up one place to fill the hole, and then reduce the array length by 1. Step 3 would be an extremely expensive gas-wise, since we'd have to do a write for every zombie whose position we shifted. If an owner has 20 zombies and trades away the first one, we would have to do 19 writes to maintain the order of the array. Since writing to storage is one of the most expensive operations in Solidity, every call to this function would be extremely expensive gas-wise. And worse, it would cost a different amount of gas each time, depending on how many zombies the user has in their army and the index of the zombie being traded, so the user wouldn't know how much gas to send. Note, of course, we could just move the last zombie in the array to fill the missing slot and reduce the array length by 1, but then we would change the ordering of our zombie army every time we made a trade. Since view functions don't cost gas when called externally, we can simply use a for loop to iterate the entire zombies array and build an array of the zombies that belong to this specific owner. Then our transfer function will be much cheaper, since we don't need to reorder any arrays in storage, and somewhat counterintuitive, this approach is overall cheap. Using for loops. The syntax for for loops in Solidity is similar to JavaScript, so let's look at an example where we want to make an array of even numbers. For, we declare our counter, we have an exit condition, and then we have an incrementer. So then we do work inside, and that's it. That looks just like what we would do in JavaScript. This function will return an array that has the contents 2, 4, 6, 8, 10. Cool. Put it to the test. Let's finish our getZombiesByOwner function by writing a for loop that iterates through all zombies in our DApp, compares their owner to see if we have a match, and pushes them to our result array before returning it. Number 1. Declare a uint called counter and set it equal to 0. We'll use this variable to keep track of the index in our result array. declare a for loop that starts at I equals 0 and goes up through I is less than zombies.length. This will iterate over every zombie in our array. Inside the for loop, make an if statement that checks if zombie to owner I is equal to _ owner. This will compare the two addresses to see if we have a match. Inside the if statement, add the zombie's ID to our result array by setting result counter equal to I. Increment counter by 1. See the for loop example above. That's it. The function will now return all the zombies owned by the owner without spending any gas. Love it. Let's start at number 1. We will declare a uint called counter, and we'll set it to 0 to start. Next, we're going to declare a for loop that starts from a uint I equals 0. Then we will stay in here as long as I is less than zombies dot length. Looks just like JavaScript. And then each time we go I++. Curly braces, we've now got a for loop. Inside the for loop, we want an if statement that checks zombie to owner I, so the ID of the zombie equal to owner _ owner. Now our curly braces finish up our if statement. Inside of our if statement, add the zombie's ID to our results array, so we have a result dot push we don't want the push, we want to set the actual value of counter equal to I, and then we want to say counter ++. That's it. Got it. Wrapping it up. Congrats, that concludes lesson number 3. Let's recap. We've added a way for our CryptoKitties to update our CryptoKitties contract. We've learned to protect core functions with only owner. We've learned about gas and gas optimization. We've added levels and cooldowns to our zombies. We now have functions to update a zombie's name in DNA once the zombie gets above a certain level. And finally, we now have a function to return a user's zombie army. Claim your reward. As a reward for completing level 3, both of your zombies have leveled up. And now that No Name, the kitty zombie you created in level 2, is upgraded to level 2, you can change the name to give him or her a name. No name, no more. Go ahead and name your No Name. No name, no more. At Voice First AI. Boom, updated the name. Proceed to the next chapter. Congrats, we completed lesson 3 of CryptoZombies. This lesson was much more technical. I felt myself dozing off a little bit. I'm going to register so that those registration notices don't keep popping up. This was a cool lesson to understand gas costs, mostly understanding gas costs as well as how to update a smart contract that's been deployed on Ethereum. I'm now curious, when we do deploy our first smart contract for Alexa for musicians, what is the blockchain we should use? Should we be writing directly to Ethereum, or should we be leveraging a layer 2 blockchain that is built on top of Ethereum so that we're still leveraging the security of Ethereum with lower gas costs? Or should we just move away from Ethereum completely and find a totally separate blockchain that's unrelated to Ethereum to host our dApps for publishing? That's it. If you got any questions, just leave us a comment or message us on any social media platform at Voice First AI. And that's it. Hope you enjoyed the video. Talk to you next time.